Hi guys, assalamu alaikum. I hope you're all well and having a good day. In our last video, we have solved all the important and common questions of electricity. Now in this video, what we are going to go through is the waves. As the title suggests that we are not only going to go through the waves common questions as well as the important questions for your upcoming exams. And if you haven't watched the electricity video yet, then please check the description box. I will be providing the electricity video in the description box. Hopefully it will help you a lot. Now without wasting any more time, let's start. This question number 13 says a glass is filled with transparent hydrobates. The glass is then half filled with water. The beads under the surface of the water seems to disappear. So basically when the beads are in contact with the water, they are disappearing, right? This is how you should annotate in the exam day as well, because it will be easier for you to remember those things. Now it says the refractive index of the hydrobates is similar to the refractive index of water. Now this information is extremely important, that both the hydrobates and the glass have the same, both the hydrobates and the water, both of them has the same refractive index. Explain why the hydrobates are difficult to see when surrounded by water. Now they're asking why they are difficult to see when they are surrounded by water. Now let's think it of like this. Let's draw a normal line, and now let's say a light. This is the angle of incidence, right? This is the angle of incidence. Now if it refracts, it will move like this, right? It will move like this, right? If it refracts, if it will move like this, or maybe it will move like this, right? It will not go straight. It will not go straight. If it will move like this, and if it moves like this, some of the light will be reflected as well. Some of the light will be reflected as well. If there is a refraction, then there is a high probability that a little amount of light will be reflected as well. And when a light reflects, only then we see something, right? When the light reflects, we see something. Don't get worried about it. We will explain it in a real detail. Just wait for a few minutes. Now just understand one thing, that when something reflects, at that point only we can see that particular thing. Now let's have a look at it. Now as it has refracted, it will reflect a little bit. Now if it doesn't refract at all, if it goes straight like this, if it goes straight like this, then the reflection is zero, because it doesn't reflect. And when something and if the light doesn't reflect of something, we don't see that particular thing. Now let's say you are standing right here and you are looking at this place. Okay, now when you are looking at this place, the light is going like this, the light is going like this. And when the light has gone like this, rather than reflecting back, it move straight from the water to the glass beads. There is no refraction. There is no refraction, as well as there is no reflection as well. As there is no refraction, as it goes straight, as there is no refraction, as it goes straight, there is no reflection as well. And as there is no reflection, you cannot see the hydrobates. Why there is no refraction? Because the refractive index of both the hydrobates and the water is the same, and when both of them have the same refractive index, the incident angle is going to be equal to the angle of refraction, or the refracted angle. And the light from the observer side is transmitted and not reflected. The light will be transmitted like this. It will not reflect back. It will not reflect back. As it doesn't reflect back, we cannot see the hydrobates inside it. Okay, and why this is? Because when they have the same refractive index, there is a very small change in the speed when it moves from the water to the hydrobates. When the light moves from the water to the hydrobates, it encounters a very small change in speed, and when there is a very small change in speed, we can say there is not much difference. Now here you guys can check the answer. I have written there is little or no refraction. We know there is no refraction, that's why and there is also no change in direction of the light, right? The light was straight going through the origin. It was straight going like this. There was no change in the direction of the light. The incident angle is equals to the angle of refraction, and light from the observer side is transmitted and not reflected. This light goes straight. It is not refracted or reflected, it is transmitted, so it goes straight. This is because there is only a small change in the speed, no change in the speed of light. As there is no change in the speed of light, that's why it goes straight. And why there is no change in the speed of light? Because the refractive index is the same at the boundary between water and the hydrowaves. Now out of this all 5 points, you guys will have to only write 2 points. But the reason behind giving you guys all of these 5 points is because so that you guys can understand this concept in real detail. Now we will go through another question like this, which one was in a recent paper as well. A similar question says the photograph shows a hand holding in a glass beaker containing water. Fingerprints are a series of ridges and valleys on the surface of fingers. The valleys trap air when the fingers presses against the glass as shown in the diagram below. So we can see clearly right here the finger is in contact with the glass, but here there is no contact. Here as well there is no contact, but here there is a finger in contact with the glass, and when there is a finger in contact with the glass, it produces a dark region, and here when there is no contact, it produces a light region. This is what it says, right? Light in the water is incident upon the boundary between the glass and the air. The critical angle between the glass and the air is about 40 degree. Skin has a similar refractive index to the glass, the same line that we have seen in the previous question as well. Explain why the fingerprints are seen as light and dark regions. Why there are light and dark regions. You can see right here, here is a dark region, and in the middle there is a light region. There is a dark region, and then in the middle there is a light region. Now let's have a look at it, why this is actually happening. Let's relate this question to the previous one. Okay, let's relate this question to our previous answer. We can see here we weren't able to see because the light was transmitted, right? The light was transmitted from the glass to the hydrowaves, right? Or from the water to the hydrowaves. That's why we couldn't see the hydrowaves right here, because the light wasn't reflecting back. Because the light wasn't reflecting back. This is the same concept in which we will answer right here. Here there is dark regions. Why there is dark regions? Because the light is not reflecting back. And why the light is not reflecting back? Because the refractive index of the glass and the air, sorry, the reflective index of the glass and the finger surface is the same. So the light is passing through, or the light has been transmitted from the glass to the finger space, and there is no reflection. That's why there is no light. But in the air, the refractive index of the glass and the air is different. That's why as they have different refractive index, the light after going in this position, it reflects back. And when there is a reflection, you can see a bright line. But when there is no reflection, when it gets transmitted to the finger's surface, as there is no reflection, we cannot see anything in this position, so it will be dark, right? This is how the questions are repeated, but you guys are not able to pick it up. So make sure you are preparing in the best possible way so that you guys can pick this type of repetitive questions. All the questions in unit 2 are repeated, just you guys have to be able to answer it. It says some of the light traveling from the glass is this is not going to be reflected, actually, sorry, this is going to be transmitted into the finger. Dark areas where fingers are in contact with the glass, because at that place it doesn't reflect. Okay, it is this one, it is not going to be our answer. This is only the transmitted part is the correct. It says some of the light traveling from the glass is reflected from the air. Here it is reflected here, that's why we can see light areas or bright areas in contact with the glass. Okay, when the air is in contact with the glass, because air and the glass have a difference in the refractive index. That's why the light cannot pass, the light reflects, and that's why we can see a bright region right here. So a similar value of refractive index means it doesn't reflect anymore, and if it doesn't reflect, we can say we will see a dark region right here, and we will not be able to see anything because the light is not reflecting. When you are standing in front of a mirror, you see yourself because the light is reflecting from the mirror into your eyes. That's why you are able to see yourself. Otherwise, a student wearing polarizing sunglasses observe a mobile phone screen. So when you wear polarizing sunglasses, one thing that we have to understand, and we maybe know about the polarizing sunglasses because you are appearing for the exam, is the polarizing sunglasses only lets the light pass through it according to the line of plane of polarization of the polarizing sunglass. Okay, so now we will have to guess the plane of polarization of the polarizing sunglass. The student rotates the mobile phone through 90 degree. So basically it was vertical before, we can see, and then it was moved by 90 degree, and now it has become horizontal. Explain why the screen completely black when the student rotates the mobile phone through 90 degree. So the screen is appearing completely black. So when it is appearing completely black, that means um, light has been absorbed. Completely black means the light has been absorbed by the sunglass. No more light is passing through the sunglass. No more light is passing through the sunglass. And why and when does the light is completely absorbed and no more light passes through the glass? It happens only when we know we only see the screen. We will see the screen appear, let's say, bright only at that point when the plane of polarization of the light and the plane of polarization of the sunglass is in the same direction. Let's say the plane of polarization of the mobile phone is vertical right here. At that time he was seeing the screen bright, right? That means that the plane of polarization of the sunglass is vertical as well. That's why he was allowing the vertical planes of the light of mobile phone to pass through the sunglass, and that's why he was seeing the screen bright. But when the mobile phone's plane of polarization of the light from the mobile phone become horizontal, the screen become completely black. That means now the plane of polarization of the light from the mobile phone is horizontal, but the plane of polarization of the polarizing sunglass is vertical. So we know the vertical plane will never ever let horizontal plane light to pass through, and the horizontal plane light will be completely absorbed. Okay, it only allows light to pass through if it is in the same plane, just like the plane of polarization of the sunglass, which is vertical. Now let's have a look at the answer. It says light emitted from the mobile phone screen is polarized. Yes, it is polarized. This is the first line that you will have to write to get that first mark, because it's a 3 marks question and there should be 3 points. This is the first point that you guys will have to write. The second point says when the phone is rotated, the plane of polarization of the light and the plane of polarization of the polarizing filter in the sunglass are perpendicular. Yes, it was vertical and here it is horizontal. So both of them are perpendicular. When the phone is rotated, the polarizing sunglass absorbs the light. This absorb is a key word that you will have to be understanding. This perpendicular is a keyword as well, and this polarized is a keyword as well. So 3 marks for these 3 lines, and these 3 lines should include these 3 keywords. Otherwise, no matter how better you understand, if you cannot include these keywords, you will not get the mark. So make sure, as it is a frequently asked question, you should memorize the ms points. Now let's move forward to another common question. A solar cell has a thin coating of thickness d to reduce the reflection of light. White light incident on the coating is reflected from the top and bottom surfaces of the coating. This produces a final reflected beam as shown. Okay. Explain why some wavelengths of the incident white light will be missing from the final reflected beam. Now, right after reading this question, right after seeing this missing question, there is only one thing that comes to my mind. There will be either like that, thus when they will come, they will be straight transmitted through the solar cell. right? This is one thing, that they won't be reflected. This is one thing that can happen. That's why some of the incident white light was missing. Otherwise, one thing that can happen is, I will be saying later on, but the first thing that came to our mind was it will be transmitted through. But here it is not possible because there is a very high difference between their densities. There are very high difference between their densities, or the refractive index will be very different. So as the refractive index will be very different, as we have seen already previously, for a light to travel straight with a refracting or reflecting, it has to have the same refractive index as its and the other one. The coating and the solar cell would have to have the same refractive index, something that we have seen previously, right? As they both have different coating, and as they have different thickness, we can say they have different refractive index as well. So it cannot happen. Now the another thing that comes to my mind is the destructive interference. Why destructive interference? Because one light is coming right here, and it is reflecting from the bottom, and now there is another light which is coming from here, which is hitting the top and then going like this. So both of them are in phase right now. So when they're in phase, there will be constructive interference. But let's say if they are in anti-phase, the two reflected light from the top and the bottom are in anti-phase. At that time, a destructive interference will happen. And when a destructive interference will happen, some of the lights will be missing because they will be destroyed, right? And this is a 3 marks question, so you guys will have to give 3 points for this. And the first point will be superposition takes place. The second point will be the destructive interference takes place when two reflected waves meet in antiphase, and that's why the wavelengths are missing. And the third mark will be to saying this n plus half lambda part. We know in destructive interference the path difference is 2d is equals to n plus half lambda, whereas in constructive interference it is n lambda. So make sure to provide these important informations in the answer. And the reason behind it being in 2D is because the light is first coming and then it is getting reflected. Some of the students face really difficulties to understand why there is 2D in the path difference formula. In the path difference formula, there is 2D because the light is first coming and then it is reflecting. So it is covering the distance twice. Okay, it is covering this distance twice. That's why there is 2D. Now let's also go through this very repetitive question. They ask what is the difference between unpolarized light and polarized light. The main difference between unpolarized light and polarized light is in unpolarized light vibrates in multiple directions. It will vibrate like this. Okay, it will have the vibration in multiple directions, or we can say it will vibrate in vertical and horizontal plane. Only talk about, if you talk about planes, then your 3 points should be in planes. This is a 3 marks question. It can be answered in two ways. One is direction and the other one is planes. If you write the answer in terms of plane, make sure all the 3 points are in terms of plane. And if you're writing in terms of direction, then make sure your all 3 points are in direction form. And writing in direction form is easier, that's why I'm writing in direction. So basically a plane in unpolarized light, the light will vibrate in multiple directions, whereas in plane polarized light the vibration will be in one direction only. Let's say in plane polarized light the vibration was like this, it used to travel in all directions, but in a plane polarized light it will be vibrating only in one direction, and this vibration will be perpendicular to the direction of wave travel. There, let's say the wave is traveling horizontally, so the vibration will be vertical, which will be perpendicular to the direction of the wave travel. And memorizing these 3 points is extremely important for your exam day. Now this question says, describe how student can demonstrate the light from the sun is unpolarized. So if the light is unpolarized, then it will vibrate in all directions. And if you pass through a polarizing filter, let's say there are a lot of, this is an unpolarized light. If you pass through this unpolarized light, let's say through this polarizing filter, okay, uh, the plane of polarization of this polarizing filter is, let's say, in the vertical direction. So if you pass this through it, it will only show this is the polarized field, that is, this is the polarized filter that will come up, because when you pass an unpolarized light through a polarizing filter, the polarized light is produced, and the polarized light has its direction of vibration in the vertical direction, because the polarized filter also had its plane of polarization in the vertical direction. This is how you can examine. So here, to demonstrate the light of the sun, what he can do is he can direct the light through a polarizing filter, just like here we directed the light through a polarizing filter, and then we'll rotate this polarizing filter and see if the intensity of the light changes. If the intensity of the light changes, means, let's say, if the intensity changes, so how it will actually work? Let's say if this is a polarized light which is in in one direction, which is moving in one direction, like this one, and now I have set a polarizing filter right here. Okay, now the vertical plane of this, the plane of polarization of this, uh, the plane of polarization of this polarizing filter is vertical. Now if I rotate this polarizing filter and I convert, if I rotate this circular polarizing filter, at some point the polarizing filter's plane of polarization will be horizontal, which is perpendicular to the plane of polarization of the polarized light. So what will happen is the intensity will decrease. Now if it is not a polarized light, and if it is an unpolarized light, if it has the plane of polarization in multiple directions, what will happen is, no matter whether you rotate it or not, the intensity will not increase or decrease. So at that time we can say the light is unpolarized. So this is basically how you can explain. So memorizing these 3 points will be very. Now this question says a ray of unpolarized light is incident on a polarizing filter. The polarizing filter transmits light of intensity I. It has an intensity of I. The question says the polarizing filter is then rotated in the direction shown on the diagram. It is rotated anti-clockwise. Which of the following gives the intensity of light transmitted of the filter has been rotated 90 degree? Now the intensity will not change. Why the intensity of will not change? We have seen a similar question before, right? The intensity doesn't change because it was an unpolarized light. For an unpolarized light, the intensity doesn't change. Okay, no matter how much you rotate the polarizing filter. This very important question says a data logger connected to the transducer produces a graph of ultrasound signal strength against time. So this is the transmitted pulse and this is the reflected pulse. Okay, so basically let's say there is the bottom of the sea and here is a crack right here. Okay, and I will be sending a signal from this transducer. Okay, so the signal will be moving like this. Now the question is whether the signal is moving, right? The signal is moving. Now as it is transmitted and is reflected, so the signal will go and then the signal will come back. So the signal is covering the distance twice. So in this type of maths, we will write the formula speed is equals to 2d divided by time taken, because the distance has been covered twice. Once he has gone and then he has reflected. Okay, this is the main concept of this part. Now let's move forward to this question. What does it say actually? It says determine whether the reflected pulse is from a crack in the rail or the bottom of the rail. So if there is a crack, it will come back quickly, right? Because it will not reach the bottom. If there is a crack, it will come back quickly. It will not reach the bottom. So let's say there is a crack like this and this is actually the bottom. So if there is a crack, it will go like this and then it will come back like this. So the distance covered will be smaller. So as the distance covered will be smaller and the speed is constant, so the time will be less. Whereas if it has covered this distance and reached the bottom and then came back, so it will have a time equal to greater, right? So this is the time that it has actually taken. So it was from 5 to 30 microseconds. So we can say the difference is 25 microsecond is the time that he has taken to come back. Now we will use these data to figure out the expected time that it should take if it has reached the bottom, and then if this time is smaller than the time it has taken, then we can say yes, it has come from the it has come from the bottom. It has come from the bottom. But if this time is greater than the expected time to come back from the bottom, then or equal, if this time is equal or greater than the expected time that we expect it to come back from hitting the bottom, then we can say yes, it has hit the bottom. But if the time is smaller, then we can say it didn't reach the actual distance that it should have reached, so we can say it was from the crack, right? So now let's figure out this time. So we can say time is equals to 2d, 2 into 15 into 10 to the power minus 2, because it is in centimeter, divided by 5800. Our value will be around 51.7 into 10 to the power minus 6 seconds, which can be written as 52 microsecond. As this microsecond, this is the expected time that should be taken by the signal to go to the bottom and then come back. As this time is greater than the time it has actually taken, so we can say it has actually came back from the crack. So we can say this came back from the crack, right? Now this question says the simple stationary wave that can be found on the string has a node at each end and an antinode at the center. We know where there is a node, there is no amplitude, and where there is an antinode, there is a maximum amplitude, right? This is what nodes and antinodes means. But in this question it's a bit different. It says the frequency of the wave is called the fundamental frequency. Okay, great. The strings on a volume have different fundamental frequencies as shown. All of them has different fundamental frequencies. The tension in one of the string is 71.5 Newton. The length of the string is 32 centimeter, and the mass per unit length of the string is this much. They have said whether the string is 1, 2 or 3. So the main question is whether this string is, which one is this string actually, whether it is 1, 2, 3 or 4. Now to figure this out, the only data they have provided us is the fundamental frequency. So we will have to figure out the fundamental frequency of this string, which has a tension like this and which has a length of this. We know the only formula here is V is equals to F lambda, right? There is a formula V is equals to F lambda, through which we can figure out our fundamental frequency. Now we'll have to figure out the frequency, and we know V and lambda needs to be in our hand. So first of all, let's think about the wavelength value. We know there is only one loop in this stationary wave, and we know if there is only one loop, the length is going to be lambda by 2, right? The length is going to be lambda by 2. I can actually show you a few more graphs right here. You guys can see a few more graphs right here, that when there is only one loop, the fundamental frequency is f naught. At that time the length is L by 2, and when there is two loops, the wavelength value is lambda, and then when there is three loops, the wavelength value is 3 by 2 lambda. So basically the wavelength value increases by 0.5, and as the loops increases, the wavelength value increases by 0.5, and as the loops increases, the fundamental frequency increases by 1. As there is 4 loops, there is 4 fundamental frequency, and 4 into 0.5 is 2 lambda, which is 2 wavelengths. So you guys will have to be able to remember this loops to know about the lambda. So basically, as there is only one loop in this diagram, we know our lambda value is going to be lambda is equals to lambda by 2 is equals to the length, right? This is going to be the length. As lambda by 2 is equals to length, if you have to figure out lambda is equals to 2L. So we know we'll have to multiply 2 into the length to figure out this wavelength value. Now we have got our wavelength value as well. Now to figure out the frequency, the only thing we need in our hands is our velocity value, and we know they have given us the mass per unit length of the string, and there is only one formula which relates both the tension and the mass per unit length of the string, and that is V is equals to root over tension over mu. And here we can put the tension value and the mass per unit length of the string. We will get our velocity, and then we can use this velocity right here as well as this 2L right here in the lambda part to figure out our frequency. This is how we will actually figure them out, and we will get our value as 293 hertz. So we can say the string is the second string because the fundamental frequency is 294. Alright guys, so now let's have a look at a more advanced question of stationary waves. We have seen one previously, right? Now let's look at this. It says a wire is stretched between two fixed points. The wire is made to vibrate and a stationary wave is created. This produces sound wave in the air. The fixed ends of the wire acts as nodes, and there is an antinode in the middle of the wire where the amplitude is maximum, and here the amplitude is 0. A wire of length 18.7 produces sound wave with a frequency. So they have given us the frequency as well as the length of the wire. The tension in the wire is adjusted with the frequency of sound is 880 hertz. So they have given us two frequency values. Okay. Calculate the decrease in tension required to cause this change in frequency. So basically, the decrease in tension that is important to cause a change in this frequency. Mass per unit length is given. Now, one thing that we can do in order to do this question is we can figure out the particular tension for this frequency, and then we can figure out the particle tension for this frequency. And if we subtract these two tension, we will be able to figure out the decrease in tension that is required to change the frequency from 882 to 880, right? So to figure out the tension, we know we have the length, and as it includes only one loop, as we have practiced before, it will have a length of lambda by 2, and we know lambda is equals to 2L, right? Lambda is equals to 2L. Now we can derive the formula as we can write V is equals to root over tension divided by mass per unit length, right? Now this V also has a formula, V is equals to F lambda. So we can write F lambda, and we can take this root over into the other side, which will become F lambda squared is equals to 2 divided by the mu, right? And we have our frequency as for 882, we have our lambda, we have our tension that we will be figuring out, and we have our mass unit per length. So using all of those things, we can figure out the tension for this particular frequency of 882. Now let's do it. So for 882, this is how we are going to do this. First of all, using the lambda, we'll figure out 2L. We know the formula of lambda is 2L, right? So here we will multiply 2 into the length that they have given us. This is the length that they have given us, which needs to be converted into meter. They have given us in centimeter. Using this, we will figure out the tension for 882 hertz, and the value of that tension is going to be 552.8 Newton. Now we will do the same math for 880 hertz. When we will do the same math for 880 hertz, the tension will be a certain value, and if we subtract this tension value, if we subtract this tension value with this tension value, we will get a decrease in tension as 2.5 Newton. You guys will have to just subtract these two tension value. Let's say this is my tension 1 and this is my tension 2. So tension 1 minus tension 2 will give us a value of 2.5 Newton, and this is our decrease in the tension. Hopefully you guys have understood this type of maths, as they are really common in the exam papers, and you guys will have to be very good, and you guys will have to have at least a simple mentality and skill to solve this type of Very easy, but sometimes a little tricky questions. Now let's head towards something more. Let's look at another stationary wave question. It says a recorder is a musical instrument with a mouthpiece at one end as shown. So basically this is the mouthpiece, and there is an open end as well. It also said when a musician blows into the mouthpiece, a stationary wave is produced in the air column inside the recorder. So we know, as this shows, there is an antinode right here, and there is an antinode right here, and there is one node. Says there is two antinodes on two different sides. They have access to figure out the frequency of the sound. So to find the frequency, they have given us the speed of the speed of sound in air, and the length of the recorder. We know v is equals to f lambda. We got our velocity. We'll have to figure out our frequency, and to figure out the frequency, we have to figure out the length. And we know the distance between from one antinodes to another antinodes is lambda is equals to L by 2, right? Or we can say length is equals to, sorry, my bad, it will be lambda is equals to 2L, right? This is the formula. So now we can use lambda is equals to 2L to figure out our lambda value. And then when we will be done with figuring out the lambda value, we can put this speed as well as this lambda to figure out our frequency. We can divide both of them and we'll get the value as 699 hertz. Now moving on to the next part, it says on a violin, a stationary wave is created when a string is plucked. A violin string has a fixed length, but the tension can be adjusted. When a string is plucked, it produces a sound with frequency of 432 Hz. This string is adjusted to produce a sound of frequency 440 Hz. So basically you can adjust it. So to increase or decrease the frequency, we'll have to adjust the tension. So let's say this is for frequency 1, we'll have to figure out the tension 1. And for this frequency 2, we'll have to figure out the tension 2, and then we will figure out the percentage increase in the tension. So to get the percentage increase in the tension, we will have to figure out these two particular tensions, and then using these two tensions we will be able to figure out the percentage increase between these two tensions, right? Now let's figure this out. We know only formula which relate the tension with the speed is with the tension is v is equals to root over tension by mass per unit length. And now we will have to make tension the subject, so it becomes v square mu, right? And we know the formula of v is f lambda, so we can say t is equals to f squared lambda squared mu, right? And we know these both lambda and mu is constant, so the t is directly proportional to the f squared, so we can say t is directly proportional to f squared. So now to figure out the percentage increase in tension, we know always the formula that is used in percentage increase in del t. Now let's go through this very important question which says describe the motion of the air at node and at antinode. Okay, now we know this is our node and this is another node, and in the middle here is the antinodes, right? And here in the middle here is the antinodes. Now in antinode there is maximum displacement, but in node there is no displacement. There is zero displacement in the nodes. So this is how you will get 2 marks, and the third marks will be given if you guys can write that particles move in a direction parallel to the direction of the original vibrated antinode. If the original vibrated antinode is moving in the upward direction, then the particles will also move in the upward direction. They always move in the parallel direction. Okay, they always move in parallel direction. Now this question is very important because this is a 3 marks question that is more or less comes in every alternating years. So make sure you are memorizing it for your exam session, and it is not only important to memorize, it's also very important to understand this part. Now this is another very important math which asks you to figure out the critical angle, and we have to be able to figure this out because this is another very important and common question. It says an optical fiber consists of a core material surrounded by a material of lower refractive index called cladding. A ray of light approaches the boundary between the core and the cladding as shown. So basically this core is moving in this direction and it is hitting the boundary between the cladding and the core. It says show that the critical angle for light incident on the boundary between the core and cladding is 75 degree. Now one thing that you guys will have to be very sure about one thing is when something has a critical angle, when we are figuring out the critical angle, the angle of refraction is along the boundary, or the angle of refraction is perpendicular to the normal. Let's draw the normal first. So basically this is our normal, right? And when there is a critical angle, the angle of refraction is not gonna be like this. The angle of refraction is not gonna be like this. The angle of refraction will be perpendicular to the normal. And when the angle of refraction is perpendicular to the normal, we can say for this refractive index, we know the formula n1 sin theta 1 is equals to n2 sin theta 2. For this n2 is our this refractive index of 1.43, and this sin theta 2 value is going to be sin 90. Why this is sin 90? Because it is perpendicular to our normal. Okay, and our n1 is going to be the refractive index of the core, and we know the refractive index of the core is 1.48, and figuring out as this theta is what will give us our critical angle, whether it is a critical angle or not. Now let's figure this out. Here we can see that C value is 75.1. So yeah, we can show that our critical angle is 75 degree. Now this math was very important. Now let's have a go at some few more questions right there. In the next part it says, explain what will happen to the ray of light after it meets the boundary between the core and the cladding. Okay, when it hits the boundary here, what will happen to this one? The diagram is drawn to scale. You should use a measurement taken from the diagram. So as it has shown, to take a measurement from the diagram, we'll have to take the measurement from the diagram, and we know the critical angle is 75.1 degree. Now the measured angle that we will measure, if that is greater than the critical angle, there will be a total internal reflection. If that is smaller, then it will have a certain refraction, right? Now let's have a go at it. What does it say? What we'll have to first do is we'll have to draw a normal right here, and after drawing the normal, we'll have to measure the angle with the normal. This value we'll have to figure, and when you will use a protractor to measure this angle, you will find out that this theta is equals to 79 to a range of 81. Any value in between this is correct. So as this value is greater than the critical angle, we can say there will be a total internal reflection. So our answer to this, so basically this is going to be our answer, which says the angle of incidence is greater than the angle of incidence is measured as 79 degree, which is greater than our critical angle, so total internal reflection will take place by T1, right? So it will be equal to, we know for del T means T1 minus T2, and we can write, rather than T2 minus it's T2 minus T1, rather than writing T2 minus T1, we can write F2 minus F1, because tension is directly proportional to frequency. So we will write F2 minus F1, right? And this is not only F, this is actually F squared. So F2 squared minus F1 squared divided by the F1 squared, because it is tension 1. For tension 1 it is F1. Now we know F2 is 440 minus 432 squared divided by the F1 squared, which is 432 squared. So our percentage increase will be 3.73%. So hopefully you guys have understood this math as well. It was another variation of maths in the waves chapter. Alright guys, so now let's have a look at this tricky question. It says the speed of waves on a vibrating string is investigated using the apparatus shown. The length of the string between the vibrator and the pulley is L. One thing that you guys will have to understand is the length of the string is not only right here. The length of the string is from this position till this position. The whole part is the length of the string. This whole part is the same string, right? Though it is actually that is a little curved, but this is the whole length of the string. So the length of the string between vibrator and pulley is this length is L, whereas this small length is L divided by 3, and the mass of the whole string is M, and the mass of the hanging mass, this hanging mass, is the M. Which of the following expression represents the speed of the waves on the string? We know the only formula that relates the speed of the wave in the string is mu is equals to mass per unit length. Not actually this formula. The formula is velocity is equals to root over tension divided by the mass per unit length. Right here, one thing that you guys have to understand is while writing the formula of mass per unit length, you guys will always have to think the length of the string. Now here the length of the string is not only L, because the string is also right here, so we will have to add this L by 3 as well. This was an out of context question, not out of context actually. This was the thing that was a bit tricky to understand, that you guys will have to take the full length of the string. We always take the full length. In previous questions we only have seen this part. There was never a part like this in the question, right? But here, as they have this part as well, it says mass per unit length of the string. Unit length means the whole length of the string. So L plus L by 3 is 4 by 3L. Now this mass is the mass of the whole string. Yes, exactly correct. But what will be our tension? What will be our tension? The tension is acting upward, right? And the tension has been provided by the weight of this hanging mass. The tension has been provided by the weight of the hanging mass. As this tension is stretching the string like this in this direction, how is it stretching? It is able to stretch because of the weight from the hanging mass. So we will multiply this m with g. So mg into 4 by 3L divided by mass. This is actually not the formula. The formula is like this. We know the tension divided by mu, right? So our tension is this m into gravity, I mean the weight, divided by the mass per unit length, and the mass per unit length is this one, which is m divided by 4 by 3L. And we know when we divide the denominator with something, that denominator, that division can move into the numerator and multiplied with it, so it becomes 4g mg into 4 by 3L divided by m. And if you simplify it, the answer comes like this, and our correct answer is A. That was a tricky question, but it's solvable. If you use your brain accurately, if you think accurately, it's solvable. So make sure you remember this particular concept. Now let's have a look at this question. It says, in an experiment to determine the refractive index of glass, a student directed a ray of light towards a glass prism. The ray of light is shown before and after entering the prism. Determine the refractive index of the glass. This type of questions, I cannot emphasize enough how many times they actually repeat these type of questions. You must be able to answer this. And we know to figure the refractive index of the glass, we'll have to use the formula n1 sin theta 1 is equals to n2 sin theta 2, the exact formula that we have used in our last math as well. Now we know the refractive index of air is 1, and the area with and the sin theta 1 is going to be about 32, and we know the sin theta 2 is actually 50, right? We will actually take it like this, but no, you cannot take this as 32 and 50. Here is the gamble that Edexcel always plays. You will always have to take the angle with the normal. You will also have to take the angle with the normal. So we know if this as a whole is 90 degree, so 90 minus 32, this is going to be our 58 degree, right? And this is going to be our 40 degree. So now we will work with this 58 and 40 degree. This is the exact gambles that they always play, that you guys will have to always take the angle with the normal. Okay, you guys will always have to take the angle with the normal. Now it says n1 sin theta 1 is equals to n1 sin theta 2. Now in sin theta 1 you will take this 58 and the n1 is 1 because the refractive index of air is 1. And in n2 sin theta 2 we have to figure out the refractive index of the glass, and we know the sin theta 2 is 40 degree. So using all of them we will get that our refractive index is 1.32, and you guys will have to write them in the answer box. Well, the next question says, draw on the diagram the ray of light as it emerges from the prism at A. Now, I will give you guys just 2 to 3 minutes to think about it. What will be the actual answer? Just think it of by yourself by pausing the video. It will be very helpful for you guys to think about this kind of things. Think by yourself. Okay, hopefully you guys were able to answer this question. If you are not, then don't worry, I will be doing it for you right now. We know this is the glass, right? This is the glass, and it will be moving to the air, right? It will be moving to the air. We know when a particle moves from a higher dense medium to a lower dense medium, it moves away from the normal. It moves away from the normal. So it will move like this. It will move like this. It has moved away from the normal. Okay, it will be moving away from the normal. If I draw the normal as well, this is the normal and it has moved away from the normal. It should have moved like this, right? If it hadn't diffracted. Now as it has moved away from the normal, this is what shows that it has moved away from the normal, because it has moved from a higher dense medium to a lower dense medium. But here, as it was moving from lower dense medium to higher dense medium, it was moving towards the normal because this angle decreases. It should have gone like this, but it has moved towards the normal. This is one basic concept that you guys will have to be familiar with. Okay, now let's have a look at this part. It says a different prism is made up of glass with a refractive index of 1.63. Great. Calculate the speed of light in this glass. And we know the only formula that relates the refractive index and the speed of light is n is equals to c by v. And we know v is equals to c by n. As we have to figure out the v, we will write this refractive index divided by the speed of light divided by this refractive index, which will give us the value of our velocity as 1.84 into 10 to the power 8 meter per second. Alright, so now let's solve this question. It says the diagram shows a ray of light incident on a glass block. Complete the diagram to show the path of the ray as it enters the block. Use the space below for any calculations. So basically, we'll have to draw them. We'll have to complete the diagram. So to complete the diagram, you will have to use your scale and protractor. Okay, you cannot draw it simply. Now, the light is moving from a less dense medium to a higher dense medium. So it will be moving towards the normal. The first thing that we'll be doing is we'll be drawing a normal right here. As soon as we are done with drawing the normal, the next thing we'll be doing is, we know the light will be going like this, right? The light will be going like this, but we don't know the actual angle at which it will be going. So to figure out this angle, we have been given the refractive index of the glass, and we know the formula, right? We know the formula, which is n is equals to, or we can also write the easiest formula, which is n1 sin theta 1 is equals to n2 sin theta 2, right? And we know our n2 value is 1.58, and our sin theta 2 will just need to figure out this theta value, and our n1 is the refractive index of water, which is refractive index of air, which is 1, into the sin theta 1. So now we will have to figure out this value using a protractor, and this value will be probably sine 55. As it is sine 55, now the only thing that you guys will have to do is because we'll have to be figuring out this theta. Okay, you will just have to figure out this theta. If you can figure out this theta, our theta value will be equal to 31.2 degree. Now you just will draw a line by measuring the protector with a 31.2 degree. So this is going to be our 31.2 degree. Make sure you are measuring with a protractor. Okay, measuring with the protractor is extremely important. Now in the part B, it says the speed of light in a different type of glass is 1.96 into 10 to the power 8. Calculate the value of the critical angle at a boundary between this type of glass and air. So basically previously as well we have figured out how to value the critical angle, right? Now we are here thrown with a different challenge. The challenge is they have given us the speed of light in a different type of glass, and we know the only two medium that the light was traveling here is air and glass, and we know in air the speed of light is 3 into 10 to the power 8, and the speed of light in glass has been given as this. So we can figure out the refractive index of this different type of glass, because the refractive index can be also figured out using the speeds as well. So we can say n is equals to speed in air divided by the speed in glass, which will be equal to 3 into 10 to the power 8 divided by 1.96 into 10 to the power 8, and the refractive index value will be 1.53. Now as we have got our refractive index of glass, we can use that to figure out our value of critical angle. We can use the formula n is equals to 1 divided by sine c, and we know this n is going to be this value, right? So our c is going to be 40.8 degree. Alright guys, so now let's have a look at this tricky question. It says the refractive index of glass varies with the color of light. So it will actually vary with the color of light that is coming, or that is passing from the air to the glass. Now it says a ray of light is incident on side AB of a rectangular glass box. So this is my boundary on which it will be incident. The red light and violet light from the incident ray arrive at slightly different points on C and D. Let's say A arrived at this position, and let's say B is arriving at this position. Okay, both of them are arriving in different position. They have said determine the distance between these 2 points. Now to understand what I have to figure out actually became easier, because I have straight away drawn these 2 lines while reading the question. So this is how you guys should be drawing while reading the question, as well as annotating the important points. It becomes way more easier to solve this type of questions. Now I will have to actually figure out the distance between these 2 points, right? I will have to just figure the distance between these 2 points. I know this is my value, which is 6400 centimeter, right? Sorry, 6.400 centimeter, which needs to be converted into meter as well. And another thing is, if I know this line, if I connect this one, okay, if I can connect this one, and if I can know the angle of this one, because this is with the normal, I can easily figure out this value, right? I can easily figure out this value using Pythagoras theorem, right? I can easily figure out this value using the Pythagoras theorem, because I know this angle and I know this value, which is 6400. I can easily figure out this length, and if I can figure out this length as well as um, this length as well for this line, then it becomes easier to figure out the distance between these points. Okay, it becomes easier to figure out the distance between these points if we just can subtract them, nothing else. If we can just subtract them, we'll be able to figure out this thing. Now, how we will actually subtract them? We know this. We know this is our one triangle, right? And this is our another triangle, right? If we can figure out this angle of the bigger triangle as well as this size of the smaller triangle, if we subtract both of them, we will be able to get this distance between the 2 points, right? This distance between the 2 points. Now let's figure out this x part of these 2 triangles. Okay, let's figure out the x parts of these 2 triangles. Now before figuring out this x parts of these 2 triangles, we will have to also figure out, we will have to also use the formula n1 sin theta 1 is equals to n2 sin theta 2. Okay, we will actually have to figure out this formula, and we know there is also a formula which is n is equals to sine I by sine r, right? We'll have to figure out the refractive index, not the refractive index. We'll have to figure out the refracted angle. Actually, we will have to figure out this refractive angle as well as this refractive angle of this bigger triangle. I mean, there is 2 refraction, right? One is this one and the other one is this one. So to figure out the refractive angle, we'll be using the formula n is equals to sine I by sine r. So using this formula for the violet, we will use the refractive index of the violet, as we know the refractive index of the violet and the red light. So in 2 positions we will use 2 formulas, and we will get the angle of refraction for both of them. Now let's use this one, which is the violet one, which is 31.88. We know if this angle is 31.88 and this is 6.400, we can use Pythagoras theorem to use this formula. We can use tan opposite by adjacent. So using the tan, it becomes tan 31.8. The x value is 3.981. For the red light, the x value is 4.049. And we can just subtract both of them to get the distance between these 2 angles. Hopefully you guys have understood this math. This wasn't very difficult, but the only thing that you guys will have to be able to understand is there is one triangle right here, and there is another triangle which is bigger. If you guys can figure out the value of this part, you guys can figure out the value of this part as well as the whole value, then it gets easier to figure out this distance between the 2 points. It becomes way more easier to figure this out, and I hope this question was Alright, so now let's have a look at this question. It says the diagram shows a ray of light traveling from a fish to an observer. So it is traveling from a fish to an observer. Okay, so it is going from a more dense medium to a less dense medium, and it refracts at the water air boundary. It has said determine the refractive index of the water, and you should take the measurements from the diagram. Now in the recent years, these type of questions are very similar, and one thing that I want to say you guys is never ever forget to take your compass, um, protractor and scale with yourself while going into the exam day. Now let's have a look at it, how we will actually do this. They have said we'll have to take the measurement from the diagram. So to figure out the refractive index of the water, the formula of the refractive index is n1 sin theta 1 is equals to n2 sin theta 2, right? Or you guys can write the formula like this as well, which will be we can write N air sin theta air is equals to NW sin theta W. Now what we'll have to do is we'll have to put a protractor right here like this along with this normal line. This will be the protractor, and you guys will have to measure this angle. Okay, we'll have to measure this angle, and if you measure it using a protractor, it will be around 43 degree. And to measure this angle, we'll have to put the protractor like this, and the protractor will be facing like this. Then we will be able to measure this angle, which will come as 65 degree. You guys should practice it at your home. So we know the refractive index of air is 1 into sin theta 1, which is going to be sin 65 is equals to refractive index of water into the sin 43. So we know our refractive index of water is going to be sin 65 divided by sin 43. This will give you your value of the refractive index, and I'm not gonna figure out this refractive index value for you. You guys should be able to divide it and get your answer. Now let's have a look at this question. It says, in the circuit shown, the battery has negligible internal resistance. L, M, and N are identical lamps. The filament of the lamp M breaks. Identify the row of the table which shows the resulting change in the brightness of the L and N. Now the correct answer will be D. But understanding the correct answer is not gonna give you, knowing the correct answer is not gonna give you the mark. You guys will have to understand this one in real detail to be able to answer this kind of questions in your exam day. Now, how can we actually answer this question? Now have a look at it. We know this is a parallel section, right? And this whole parallel section is in series with this bulb. This whole parallel section is in series with this bulb. So if we can figure out the resistance of this parallel section, we can say 1 divided by R, resistance of Lm is 1 divided by R plus 1 divided by R. Let's say all three of them has the resistance of R, R, and R. So 1 divided by R plus 1 divided by R is going to give us the resistance of this parallel section, which is R divided by 2. Now we will add the resistance of this parallel section plus this resistance to get the total resistance in the circuit. So it will be R by 2 plus R, which will be 3R by 2. Now we have got the total resistance of the circuit when all of three of them were available. Now let's take this down, as it will be it will break. So if lamp M breaks, so now let's figure out the total resistance of the circuit. Now it has R and it has R. So now the total resistance becomes R plus R because both of them are in series. So we can say now the total resistance is R plus R. So when the M breaks, the total resistance has increased because previously it was 1.5 R when the M1 present. But here when the when the M has broken, now the total resistance has increased. Now as the total resistance in the circuit has increased, we can say the current flowing through the circuit has decreased. The current flowing through the circuit has decreased. As the current flowing through the circuit has decreased, we know voltage is equals to current into resistance. As the resistance in the circuit has increased, the current flowing through it has decreased. As the current flowing through it has decreased, we can say the voltage across this bulb will also decrease. But we're also saying the current across this bulb will decrease because voltage is equals to current into resistance. As the resistance of the circuit has increased, the current will decrease. The current in the whole circuit has decreased, so the voltage across this bulb will decrease. So its brightness will also decrease. Now here, previously when both of them were in parallel circuit, we know current is shared. So L and M, both of them used to share the current. Let's say previously the current flowing through the circuit was 2 ampere. So this bulb used to get 2 ampere and 2 ampere was shared between these two bulbs. So let's say this bulb used to get 1 ampere. Now the current flowing through this circuit has decreased. Let's say it has become from 2 ampere to 1.5 ampere. So the current in this bulb has decreased. So we can say the voltage across this bulb has increased. But now this 1.5 ampere is completely gotten by this L bulb, because this bulb is no more. So his current has increased from 1 to 1.5 ampere. So we can say as the current has increased, its brightness will also increase. So we can say the lamp L brightness increases and lamp N brightness decreases. If you find this question difficult, that's why I have written this extra note, the supplement note. You guys can go through it and read it so that it becomes way more easier to solve this type of questions for you guys. Now let's move on to this question. It says the diagram shows connected wires that carry L1, L2, L3 and L4. The currents are related by the equation L1 plus L2 is equals to L3 plus L4. Now they have asked us to answer this question. We know our correct answer is C, but we don't know why the correct answer is C, because it shows about the Kirchhoff's law. L1 plus L2 is equals to L3 plus L4. This shows the Kirchhoff's law, and we know in Kirchhoff's law the current entering the junction should be equal to the current leaving the junction, and here this dot is going to be our junction because the current is moving through here, right? The current will be moving through here. So here we can see the L1 should be L2. So here the L1 is going out from the junction, whereas L2 is going into the junction. So as both of them are different, we can say this is not going to our answer because both of them needs to be equal. And here L4 and L3 is both going into the junction, but here both of them should be leaving the junction because these two should be going into the junction and these two should be leaving the junction. Here the reason behind C being the correct answer is because L1 is moving towards the junction and L2 is also moving towards the junction, whereas L4 is going out of the junction and L3 is going out of the junction, which is equal to the Kirchhoff's law that two of them should be going to the junction and two of them should be leaving the junction, which I mean is same number of currents should be leaving the junction and entering the junction. Here I have written the explanation right here. You guys can understand this explanation by reading it. Now let's have a look at this question. It says explain why decreasing the temperature of the thermistor affects the voltmeter reading. So you guys are going to decrease the temperature of the thermistor, and we know when you decrease the temperature of the thermistor, the resistance increases. Now if the resistance here increases, this is a series circuit, right? This is a both of them are in series, and they are in parallel with this 2 kilo ohm resistor. This whole series function is in parallel with this 2 kilo ohm resistor. So as these both are in series, now in series circuit we know if someone's resistance increases, then the voltage it will be getting will also increase. So it will be getting more potential difference. The potential difference across the component increases. So as the potential difference across the component increases, the voltmeter reading will also increase. This is a rule in series circuit, because in series circuit, let's say this and this whole section, both of them are in parallel. So in parallel we know they will be getting 12 volt, and both of them together, this as a whole together will get 12 volt. Now let's say previously he used to get 6 volt, and he also used to get, the thermistor also used to get 6 volt. But now as the resistance of the thermistor has increased, now from now on he will be getting 8 volt, and now from on he will be getting 4 volt. So the voltage increases as the resistance increases in a series component. Okay, this was one important concept that you guys will have to be familiar with. And here is your answer. As the temperature decreases, the resistance of the thermistor increases, and in series circuits, the greater the resistance, the greater will be the potential difference across the component. Therefore the voltmeter reading increases. Now the next question says explain how decreasing the temperature of the thermistor affects the power dissipated by the 2 kilo ohm resistor. So basically now they are asking about the power dissipated by the 2 kilo ohm resistor. Now They are talking about the power dissipated by this 2 kilo ohm resistor. When the temperature is increased and the resistance, sorry, the temperature was decreased and the resistance increased. The temperature in, sorry, my bad. The temperature decreased and the resistance increased, right? Now the main concept that you guys will have to understand is this as a whole is a series section, but this with this one is a parallel section. This whole section, this whole series section is in parallel with this 2 kilo ohm resistor, right? And both of them are going to have equal voltage. Let's say this 2 kilo ohm will have 12 voltage and this whole series junction will have 12 voltage. So basically the voltage of this, fixed resistor is going to be constant, and we know a fixed resistor always have a constant resistance as well as the voltage and the resistance. As the voltage and the resistance of this fixed resistor is constant, so we can say at P is equals to V square by R. As both the V and R constant, the power dissipated by this 2 kilo ohm resistor will be constant as well, no matter whether the temperature decreases or increases, whether resistance increases or decreases. So we can say it like that. It will be the 2 kilo ohm resistor. The 2 kilo ohm resistor is connected in parallel, and therefore the potential difference across it remains constant. As it is a fixed resistor, the resistance is also constant. Therefore, P is equals to V square by R. The power dissipation is also. Now there is another very important part, which is the coherent. This is a question that is repeated in every exam, more or less in every exam. The coherence means having the constant phase difference and same frequency. If two waves have constant phase difference, let's say two waves have a phase difference of 270 degree, so they will be coherent if this phase difference remains 270 always. It doesn't ever become 271 or 269. This is what constant phase difference means, and these two waves will have to have the same frequency as well. So make sure you are memorizing this part for your upcoming exam. Now let's go through this question. It says boats can shelter from waves on the sea in a harbor. The diagram shows a harbor where boats can enter and leave through two gaps in the harbor wall. Now the question says describe how Huygens construction can be used to predict the shape. Now in Huygens construction we knew that every point in a wavefront, let's say this point or this point or this point, this every points in a wavefront are a source of new wave. Let's say this source will become a new wave and this source will become a new wave, and there will be a superposition between these two waves, and this superposition will decide how the next diffracted wave will be. How the next diffracted wave will be, because it is passing through the slit and they will be diffracting, right? So that will decide how the diffracting wave will be, nothing else. Each point on a wave can be treated as a source of secondary wavelets. These further wavelets interfere. There will be a constructive or destructive interference between them, and whether there will be a constructive or destructive interference will decide how the shape of the diffracted wave fronts will be. So make sure you are memorizing these 2 points, because this is a common question as well. Let's start with this question. It says two waves of wavelength 12 centimeter leaves a source in phase. So when they were leaving, they were in phase. The wave travels along different paths to a point x. The path difference is now 8 centimeter at x. Now they have asked us to figure the phase difference between the two waves at x. Now to do this math, we know our answer is going to be C. But how it is going to be C? That's what we'll be doing the working. Okay. Now let's think it of that phase difference are always measured in pi, right? And the path difference is measured in lambda. So we can write, as there is both phase difference and path difference in this question, they have also said about the path difference as well. So we can write path difference is measured in lambda. So we can write path difference divided by wavelength and phase difference divided by 2 pi. Okay, because 2 pi means 360 degree, and let's say one wave. Let's talk about one wave. Okay, let's talk about this one wave. This one wave contains either 2 pi, or you can say it as a lambda. If it is about the path difference, it is 2 lambda. If it is about the phase difference, then it is, sorry, if it is phase difference, it is 2 lambda, and if it is path difference, then it is a lambda difference between them. right? So we can talk it about like this. Now we know the wavelength was 12 centimeter and the path difference was 18. So we can say here we'll be dividing, we can write del x by lambda is equals to theta by 2 pi, and we can write for this del x it will be 18 divided by the lambda, which will be 12, is equals to theta by 2 pi. Now this 18 by 12 will become 1.5, which is equals to theta by 2 pi. So now our this theta is going to be equal to 3 pi. Why 3 pi? Because 1.5 into 2 pi multiplied. So we have got this theta as 3 pi. But now here we have got the value of phase difference as 3 pi. But our answer is only pi radians. Then why did we write pi radians rather than writing this 3 pi? Okay, the reason behind that is whenever we calculate the phase difference, okay, we will sometimes get a value greater than the 2 pi. 2 pi is one cycle, right? Sometimes we will get a value greater than this 2 pi. Let's say it can be 4 pi, 5 pi, or even 3 pi. Now whenever we will get a value greater than the 2 pi, we will subtract that value from the 2 pi. Okay, we will subtract that value from the 2 pi, because the phase difference is always in the range of 0 to 2 pi. It cannot be greater than that. The phase difference cannot be greater than that. So if we get a theta value greater than 2 pi, we will subtract that value from 2 pi. So 3 pi minus 2 pi is only pi radian. Okay, this is the main thing, and the reason behind that is because the phase differences are always expressed within one cycle from 0 to 2 pi. You cannot show a phase difference greater than this 0 to 2 pi range. It has to be in between this range. Okay, that's why pi radian is our correct answer, as we have subtracted the greater value that we have gotten from 2 pi to get the pi radians. Two waves with wavelength lambda are produced by the same source. The waves travel at a different distance and then meet. At the point where they meet, the path difference between the wave is lambda by 8. Now they have asked what will be the phase difference in radians between these two waves at that point. We know the path difference is always denoted in lambda, right? And the phase difference is always denoted in radians. We know phase difference is measured in 2 pi. For a complete cycle, the phase difference is 2 pi. And for a complete cycle, the path difference is lambda. Now here, as they have divided the lambda by 8, as the lambda was um, 1/8 1/8 of its initial value. Now we will also divide this 2 pi by 8, because as the wavelength or the path difference has decreased to its 1/8 value, the phase difference will also decrease to its 1/8 value. So we will divide it by 8. So now it becomes, if we remove both of them, it says 1 divided by 4 pi. So our correct answer will be B. This was a easy peasy lemon squeezy question. Now this question says explain how a stationary wave forms on the string. We know for a stationary wave to form, this is the first wave that will be going and it will be hitting the pulley. After hitting, this wave will be reflecting back, and while this while this reflected wave will be incoming, or the reflected wave will be coming, at that time another second wave will be going, and there will be a superpose between these two waves. One is the reflected wave and the other one is the second progressive wave, and between these two waves there will be a superposition, and that superposition will produce stationary wave, or you can also say there will be an interference between them. The answer will be like this, and both of these will have the same frequency and the constant phase relationship. Okay, this 3 marks question is very important to understand. and make sure not to lose marks on this. So after understanding, memorize. Explain why ultrasound used to detect cracks in metals beams usually has frequency rather than kilohertz. Okay, megahertz rather than kilohertz. So we know megahertz is greater than the kilohertz. So basically the frequencies are greater. They are saying that the frequency, why is the frequency greater? To detect cracks. So we know if the frequency is greater, the lambda is going to be small, right? Because the frequency and wavelength are in inversely proportional. If the frequency is greater, the wavelength is smaller, and we know the smallest wavelength a particle has, the better it can detect the structure of the cracks, right? We will grade the structure of the track in more detail, right? This is what the de Broglie wavelength has said. The smaller the wavelength, the greater it will diffract when you will pass it through the slits, and the greater it diffracts, the better resolution of the cracks we will get, or the better structure of the structure of the tracks we will be able to figure out. So this is going to be our answer. Greater level of detail is possible, and the greater the resolution is, the smaller the wavelength. And the reason behind smaller wavelengths is because higher frequency. The stationary wave on the string causes sound waves to be transmitted through the air. Describe the similarities and differences between the stationary wave on the string and the sound waves transmitted through the air. Okay. So basically, the stationary wave on the string will cause the sound wave, right? So both of them are coming from the same source, right? The string. Both of them are coming from the same source. Whether this is the stationary wave on the string or the sound waves produced from the string, both of them are coming from the same source. So we can say they will have the same frequency. So both the stationary wave and sound wave have the same frequency as they come from the same source. But their speed and wavelength will be different because the stationary wave doesn't actually move forward or backward, right? Let's say the stationary wave is like this. The stationary wave doesn't move forward or backward. So we can say the stationary wave speed is, let's say there is no speed, but the sound wave is a longitudinal wave, so it moves and its speed differs in different mediums. So we can say the speed are not the same. They have said about the difference. And talking about the wavelength, we know for the wavelength of a stationary wave, the wavelength is the difference between the distance of from one antinode to the other antinode. This is what the wavelength of the stationary wave is. But the wavelength, basically the wavelength doesn't change. This wavelength doesn't change. Whereas the sound wave, the wavelength is the distance between the two compressions and rarefactions, and it actually depends on the frequency and the speed. So basically both of them doesn't have the same wavelength. The wavelength of the longitudinal wave, which is sound wave, changes depending on the medium, but the wavelength of the stationary wave is constant. So we can say the speed and the wavelength of both the stationary wave and sound waves are different. Okay, the next point that we can say is sound waves have the same amplitude at all points and stationary waves do not. The sound waves are longitudinal waves, so it will have the same amplitude of vibration while it is moving, but the stationary waves has no amplitude right here, but it has an amplitude right here. It also doesn't have any amplitude right here. So at all points means at all points the sound will have the same amplitude, but in the stationary wave at different points, let's say here, here, or even here, they have difference, that they have different amplitudes. The next point says sound waves transfers energy and the stationary waves doesn't. As the stationary wave doesn't move, so it will not transfer any energy, whereas the sound waves transfers energy as it vibrates perpendicular to the wave travel. Now the waves on the string are transverse and the sound waves are longitudinal. As it was a 5 marks question, this was exactly the 5 points that you guys will have to give. So it is very important to memorize them after understanding. Now this is another very typical question which says monochromatic light travels through air and enters a glass block. Something that we have seen in a lot of refraction questions, right? It says which quantity doesn't change. We know always the frequency doesn't change. Why the frequency doesn't change? Because the frequency comes from the source and it is not changing. It depends on the source, not on medium, whether it is entering into an air from a glass or a glass from a air. It doesn't change because the frequency solely depends on the source rather than the medium to which it is traveling or the medium to which it is right now. Now this is another very important question which says when longitudinal waves pass through a material, compressions and rarefactions are formed. Now a lot of people thinks that compressions and rarefactions are related to the displacement. No, the displacement is related to the amplitude, but the compressions and rarefactions are related to the pressure. Where there is a rarefaction, there is less pressure. Okay, the first point says compression are points where the displacement of a particle is maximum. No, it's not about the displacement, it's about the pressure. So our correct A is gone and C is gone as well because it also involves displacement. Whereas it says compressions are a process where there is a minimum pressure. No, compressions is where there is a maximum pressure, and rarefaction is actually the thing where there is a minimum pressure. So our correct answer is going to be D. So please make sure that you are understanding this concept. Alright guys, I hope you have been enjoying the video so far. If everything is making sense and you want to solve more question papers with me, you can join my question papers marathon course, which is always held 15 days or 1 month before every exam session. You can join for physics unit 2, 3, 4, 5 and 6 for this May 2025 exam session, or for all the units before your upcoming exam session of let's say October 25 or any upcoming session. And if you have got around 4 to 6 months left for your AS or A2 exam, you can join my high impact crash course, which is perfect for you if you have around 4 to 6 months or around 3 to 6 months, where we will actually complete the full syllabus together and solve all recent question papers from Jan 2020 to Jan 2025 under my personal guidance. You will also get booklets, digital notes, exclusive resources, the chance to give AI generated mocks, and also mock solving classes. So don't wait, check the number, check the WhatsApp number provided in the description box, or you can also message us in our Facebook page, Exam Essentials, to join and master A-Levels Physics with your favorite teacher Shubhra Ahmed. This question says a ray of light is incident on a glass block as shown. Which of the following doesn't occur when the ray of light is incident on the glass block? We know when it is incident, it can be totally internally reflected, or it can also be refracted, right? It can be refracted and reflected. But now the confusion arises whether it will be diffracted or polarized. Now one thing that you guys will have to know is it can be polarized. Okay, the reflected light is polarized. When a light reflects, if you put a polarizing filter ahead of this, it can be polarized. It can be polarized. Or if you can pass through a if you can pass it through a polarizing filter, it can be polarized. Why it can be polarized? Because the wavelength of this light and the wavelength of this light or the speed is the same. That's why it can be polarized, but it can never ever be diffracted. To be able to diffract, you will have to pass it through a slit, and here you are not passing through a slit, you are incidenting it on a glass block. Now this question assesses your understanding of the total internal reflection. It says a ray of light is incident on the boundary between two materials X and Y as shown. The refractive index of value for X is Nx and material Y is Ny. Which of the table give the conditions required for the total internal reflection? We know if a particle is moving from X to Y, for a total internal reflection, it should be moving from more dense medium to a less dense medium, right? It should be moving from a more dense medium to a less dense medium. This is the first criteria. And the second criteria is the angle of incidence should be greater than the critical angle. That's why our answer A is correct, because it shows like this, that the density of x is greater than y, and also the angle of incidence is greater than the critical angle. This is the main information that you guys will have to be familiar with. Alright guys, so let's start the session with a very important question. Here you guys can see at the first that I have shown the answer, which I usually don't do. The reason behind showing the answer right here is, no matter whether I show you the answer or not, if your concept is not clear, you will not understand this answer as well as the question. Now you guys can see here is a graph written like this. Now let's draw this graph by ourselves. Okay, now let's draw this graph by ourselves. We can actually draw it like this. Okay, so basically this is how the graphs are, right? I'm not that good in drawing, so please pardon me for that particular reason. This is the graph that they are showing, right? Now here, this is the y-axis, right? And from the y-axis, both the black graph and the blue graph has started. Now let's analyze the blue graph first. Let's analyze the blue graph first. Now in order to analyze the blue graph, let's take, this is the position from both of the graph has started, right? No, this is not the position from where they have started. You have guessed it wrong. This is the position from which the black graph has started, from the origin. But the blue graph actually started from this position. The blue graph has started from this position because it is its maximum amplitude or maximum vertical displacement. But here, this is the position from which it started. Okay, from the x-axis. You can say from y is equals to 0, from y is equals to 0, because this is showing us our displacement, right? So this is the position, or this is the position at where displacement is 0. So any graph starts from when the displacement is 0, not from the displacement of maximum displacement. Okay, not from the maximum displacement, it always starts from the 0 value. Now what we can do is we can draw a graph right now. We can actually do some rough works right here. The rough works will be, let's take this, let's draw another graph right here. Here what we'll do is we'll put it right here. So basically this is how the graph looks, right? Now in this graph, we know from this position to this position, this is one complete cycle. This is one complete cycle. And we know this is called as 2 pi. And we know this is known as pi. And if we talk about this half part, only this region, if we talk about only this region, this is said as pi by 2, right? This is known as pi by 2. This is known as pi by 2. Now we can denote this blue graph as our x and the black graph as our y. Okay. Now as we know, the x graph actually didn't start from the maximum displacement. The graph never ever starts from the maximum displacement. It starts from the displacement is equals to 0. So it actually started from right here where the displacement was 0 for the x graph. Now as it has started from here, we can see one thing. The question says, which of the following statements correctly describe their phase relationship? Now the answer is x is pi by 2 radians ahead of y. So basically what does that actually mean? What does that actually mean? That actually means that at the point when y was in 0 displacement, or when the y just started, when the y just started, at that time the x was at its maximum displacement. The x was at its maximum displacement, and we know to cover this maximum displacement it has covered this pi by 2 distance. It has covered this pi by 2, right? It has covered pi by 2. When you start from here and you reach, let's say you have started from here and you have reached this position, that means this is what pi by 2 means, right? And now here as well, it started from here and it has reached this position, so it has covered pi by 2 greater, right? It has covered pi by 2. It has a greater phase difference of pi by 2, because when y was at its as when the y was at the start, when the y just started, at that time x has reached its maximum displacement. That's why we can say x is greater, because x has already reached its maximum displacement, whereas the y just started. And how much ahead the x is pi by 2 ahead of y. And when they will give us a question of displacement time graph, we will always compare them vertically. We will always compare them vertically, that x is at 0 displacement and y is at vertical displacement of maximum displacement of sorry, when y is at 0 displacement, when it just started, the x is at vertical displacement. That means it has already covered this extra pi by 2 distance. Now let's look at a very similar question, which is question number 4 on another year, which said the question at first glance might look just like the previous one. Try to figure out the difference yourself. It says about the phase relationship between x and y. The question is exactly the same, but here the quantities that they have given us is displacement and distance. Now please write this down in a corner in your copy, that when they compare about displacement time graph, we compare them vertically. We compare the two graphs vertically, but when they say displacement distance graph, we compare them horizontally. So when we will compare these two graphs horizontally, now let's have a look at this, how we will actually cover them horizontally. Okay, how we will actually cover them horizontally. Now the first thing that comes to my mind is horizontally, when we will compare, this y is right here, right, at the start, but the x is right here. The x is right here and the y is right here. You guys can stop thinking about this part. Okay, this part is no more important, because now we are only looking after the horizontal path. Now the more you are in the right direction, the more you are in, when you are, the more you are far right, the more you are in the right direction, the greater is your value, right? Let's say this is the -2 value and this is 0, so 0 is greater than -2. So here you guys can see this y is at a greater is in a better position, or is, we can also say the y is ahead of x in terms of the horizontal part. In the horizontal part, the y is ahead of x because it is at, let's say, 0, and it is at -2, so 0 is greater than -2, right? So y is ahead of x, and when y is ahead of x, and how much are the difference is how much? The difference is this distance, which is like this. This is the difference that they have, right? This is the position where y is, and this is the position where, sorry, this is the position where x is, and this is the position where y is. So we can say y is this much distance ahead of x, and this much distance is known as pi by 2 that we have previously figured out, right? So our answer will be here y is pi by 2 ahead of x. Now the difference in these two questions has been this time and this distance. When there is a displacement time graph, we will compare vertical, and when there is a displacement distance graph, we will compare horizontally. Now this is not the end. Now let's have a look at a similar question like this, which we have seen in another year. It says waves can be represented on graphs of displacement against distance and displacement against time. Which of the following properties can only be determined by combining information of both the graphs? Okay. It says which of the following properties can only be determined by combining information for both graphs. So you will need the information from both the graphs to calculate that thing. Now let's think about it. We can find the wavelength and amplitude from a displacement distance graph. Wavelength and the amplitude. We can figure out the wavelength and the amplitude from the displacement distance graph. We know displacement, this is a displacement distance graph, and from this displacement distance graph we're comparing it like this, right? We're comparing horizontal, and horizontal part is the x-axis. We're comparing these two, x and y, in the x-axis. So when we are comparing in the x-axis, we are comparing the distance, right? And distance in the waves is also known as the wavelength, or you can also say it as amplitude, okay, from the displacement distance graph. But right now here it says we can find out time period and hence frequency from a displacement time graph. You can figure out the time period as well as the frequency right here. How you can figure out the time period? Because here the x-axis is time, so we can figure out time period and frequency. When you can figure out the time period, you can also figure out the frequency. Now another thing that we have understood is it actually depends upon the x-axis. If the x-axis is a distance, then we can figure out the displacement, we can figure out the amplitude and the wavelength, because distance and amplitude and wavelength both have their units of meter. Whereas the time itself says that we can figure out the time period and frequency, because time period and frequency have a formula, f is equals to 1 by t. Now we can figure out the amplitude from the graphs, we can figure out the frequency from the graphs, we can figure out the wavelength from the graph. The only thing that we can figure out from both the graphs, okay, combining, is speed is equals to frequency into wavelength. Because if you can have the frequency from the displacement time graph, if you have the frequency from the displacement time graph and you have the wavelength from displacement distance graph, you can combine both of these graphs to figure out a value. And they have asked which can be determined by combining information from both the graphs. So you will have to be combining the information from both the graphs to calculate a unit, and that unit is gonna be the speed, because amplitude is not something that you will have to find by combining both the graphs. You will just get it from one graph, which is the displacement distance graph. So now from all of these things, two things that we have understood is, if the graph is a displacement time graph, then we will compare them vertically. If this is a displacement time graph, we will compare them vertically. And if it is a displacement time graph, this graph will help us to figure out time period and frequency. The easiest way to remember is, as the displacement time graph, in the x-axis there is a time, so the time will help us to figure out the time period. And in a displacement distance graph, we will compare them horizontally. As we will compare them horizontally, here the distance is the main important thing. So as the distance is there's the distance in the x-axis, we can know another thing, that using this graph we can figure out the wavelength and amplitude from the displacement distance graph. And if we have to find something combining the informations from both the graphs, then we will be able to know that speed is equals to frequency into wavelength. We can multiply frequency with wavelength. So these are all the things, and there is very important 3 rules that you guys will have to remember, and this will be extremely important for your exam. So please review this again and again before exam. And if you have any problem understanding this one, please comment down below. I will love to make you understand again through the comments, or you can join my courses. Alright, so now let's have a look at this question, which is similar to the one that we have seen just now. It says 2 waves from the same source arrive at a point with a path difference of 3 lambda by 2, while lambda is the wavelength. Which of the following is the phase difference of the wave at this point? Now we know they have given us the path difference. According to the formula that we have been going through previously, this 3 lambda by 8 means this whole value. This is the actual path difference, right? Path difference by lambda, which is 3 lambda by 8. And we know 3 lambda by 8 is equals to phase difference by 360 degree. You can also write it down like here, that 3 lambda by 8 is actually our phase difference. Now as the formula suggests, path difference, my bad, as the formula suggests, 3 lambda, path difference divided by lambda. So 3 lambda by 8 divided by this lambda becomes 3 lambda by 8 lambda into this 360 degree will give us our phase difference, which is 135 degree, because both the lambdas get cancelled out and it remains 3 by 8 into 360. So our correct answer is C. Now this is the type of questions that they are asking repeatedly, so make sure you are understanding it completely. And if you have any problem, don't forget to comment down below. Now let's have a look at this question. It says explain why a series of bright dots is seen on the screen. The reason behind seeing a bright dot is something we have solved this question previously as well, right? The bright dots means waves from different slits met and there was an interference between them, and that interference must be a constructive interference, and their interference was in phase. That's why bright dots was seen. And if there was a black dot or a dark dot, we could have said that yes, there was an destructive interference. And for another mark you can say the phase difference is n lambda, right? Oh yeah, sorry, the path difference is n lambda right here. You can also write it down like this. Okay, you can write 2d is equals to n lambda, but for destructive interference, the previous question that we have solved, 2d was n plus half lambda. So this is the main difference between them. This is another very easy common question of Edexcel Levels Physics Unit 2, the difference between transverse wave and longitudinal wave. This is an O-level stuff, but still a lot of students face difficulties to answer this. Your answer should be aligning with the MS points. It says transverse wave oscillates perpendicular to the direction of energy transfer of the wave, and longitudinal wave oscillates parallel to the direction of the energy transfer of the wave. So please try to remember this one. So this is another very contextual question. In physics unit 2 you will be asked with some contextual questions, so make sure you are familiar with the syllabus. It says the wave fronts diffract as they pass through each gap, in which diagram it will not be diffracted like a semicircle. Now, to be able to diffract like a semicircle, the wavelength should be equal or smaller than the spacing between the slits. Now, if you use this to measure using a scale, you will see that both of them are more or less same. And here the wavelength is even smaller than the slitting between the spacing of the slit. So here there will be semicircular diffraction as well, like this. But here you guys can see the wavelength is way greater than the spacing. So when it will be traveling, there won't be any semicircular diffraction because the wavelength is greater. For a semicircular diffraction, the wavelength needs to be equal or smaller than the spacing between the slits of the diffraction grating to be able to diffract. Now this is the same question that they have asked in a different way. Now here it says describe how the teacher can demonstrate that the lighter from the laser point is plane polarized. This is the same question I have shown you guys previously, right? You guys will have to just pass it through a polarizing filter and then rotate the polarizing filter. If the rotation of the polarizing filter decreases the intensity or changes the intensity, we can see that the light is plane polarized. Now this is another very easy question. It says rolled. This is actually common with the one that we have done previously. Rolled steel joists are used in the construction of buildings as shown. The strength of an RSG is greatly reduced if there is air gaps between the steel. Ultrasound is used to detect any air gaps in the RSG. Pulses of ultrasound are sent by transducer into an RSG as shown. Any returning ultrasound is detected by the transducer. Explain how this arrangement can be used to show whether the RSG contains an air gap. So basically, if it comes back quickly, then we can say it didn't reach the bottom of the steel or the far end of the steel. That means it was stuck with the air gap before, right? This is one thing that we can think it of. Or you can also think it of like this, that the pulses of ultrasound that are sent are partially reflected. Some of them will be reflected, right? The pulses that will be sending, they will come and then they will be reflected. We will measure the time for the signal to return. We will measure this time, and we will also calculate the distance traveled by the pulse using the time measured. We will calculate the distance using the time measured because we know the speed at which we are releasing the ultrasound. As we know the speed and we have measured the time of it being going and then reflecting back, we can easily figure out the distance traveled. And if this distance is less than the thickness of RSG, we can say that there is an air gap present because the distance would have been equal than the thickness if it had traveled till the far end. But if it is small, then we can say yes, the thickness is then yes, there is a gap present. That's why it couldn't travel the far end. So this was another very easy and common question which was previously we have solved it previously as well, but that marking points were a bit different because here the main thing is about the thickness, and there maybe the thing was about the crack, that if they can hit the crack then they will travel lesser amount of distance. Let's say this is the far end and this is the crack. So if you come back quickly, then we can say you have traveled less distance. Okay, but here as it is traveling through, because there is an air gap, so as there is the air gap, it means that the wave will come like this. The wave will come like this, and then hitting the air gap, it will be again reflected. So it doesn't go through the whole thickness of the steel, right? It doesn't travel the whole thickness of the steel. So that is what they said. If the distance is less, so if it only travels this distance, then the distance is less, right? But if it had traveled the whole distance, the distance would have been greater. And we have calculate the time, and using that time and the speed we can figure out how much distance he has actually covered. Okay, this is how we actually um, explain them. Here the thickness was in order to make you understand that they have covered whether the whole part or only a small section. Alright guys, that's a wrap for today's session. I have tried my best to cover all the tricky and important types of questions that could come on your exam day. Now it's your turn to understand everything, practice hard, and make sure to go through all the recent question papers from Jan 2024 to Jan 2025. These four sets are super important. They are contextual, concept based, and will really test your basics. So revise them thoroughly and make sure you attempt the exam practice questions before stepping into the exam hall. Best of luck guys for today.